Energy and energy transformations. We've already touched on energy to begin with, so you've got a bit of a background in this. What we want to start doing is looking at energy in a variety of forms, stumbled on that word, and discuss energy efficiency and look on convergence and see what form waste energy takes in our society and how scavenging and regeneration systems work to improve efficiency. We've already been taught, or I taught you, that work is considered force times distance. It would have units of newtons times meters. You say that Newton meters, and we've nicknamed it the joule. You eat about 10 million joules a day. What does this formula work for? Any general force capable of moving an object, a specific physical distance is traveled. Notice I said moving an object. Usually forces accelerate, but frictional force, you can be fighting it quite vigorously and not accelerate. So I've gotten away with saying moving, not accelerating. Cup of coffee doesn't work. Setting fire to a sparkler doesn't work. There's nothing accelerating. We can take this formula and expand it to several specific cases. If we simply saw an object accelerate, we spotted its acceleration, we saw the distance it crossed, we can calculate the work. There is no joulometer on your dashboard. You can get the acceleration and distance from your car's speedometer, and from there you can compute the work. If instead we're fighting gravity, we just change the acceleration to g, and distance is better expressed as height. And this one is needed because planets suck. Frictional force, we've already done that one to death. So frictional force times distance, it's a force times distance. Okay? And this is because life can be a drag. And finally, who doesn't like trampolines? Of course we want to study springs. Springs lead us to like trampolines, towel snapping somebody, springs in the eye, bows and arrows. So these are all just four specific cases of this one. What if we're not accelerating, we're just moving? Like someone throws a ball at your head and it hits your head. They go think fast, throw it at you. Half mv squared is what the kinetic energy is. I forgot my little k here, but you guys don't like subscripts anyway. Here's the proof if you want. It's not necessary. Acceleration is delta v over delta t. Distance can be expressed as the average speed times time. And what's an average? You add two numbers together and divide by 2. Looky here, we've got a cancellation. So the time vanishes. I move the 2 out to the front to get it out of the way, and we'll expand this a la grade 10 math. And this happens to be what's called the difference of squares. Because this is a minus and this is a plus, we get a term right here that cancels itself out. And let's face it, in any of these kinetic energy problems, we typically start from rest. So those numbers are gone too. This leaves us with 1/2 v squared. We drop the final because if there wasn't a starting speed, why do we need the subscript? 1/2 and m over 2 are the same thing, just arranged differently. So a most common use of this is kinetic to gravitational potential energy conversion. We drop a rock, we want to know how fast it's going when it hits the ground. I'm sure that's what you've thought every time you spin over a cliff or dropped a stone or something like that. Geez, I wonder if I could calculate the actual impact speed. I mean, who wouldn't want to? And I call this the Lord of the Flies conundrum. I've readapted the commentary on our violent nature to include a warning of listening to music while on an island of savage Boy Scouts without adult supervision. So this guy is criminally planning to push a rock on this man down here. But I'm making a kinder, gentler, more modern version of Lord of the Flies where the little SOB at the top of the cliff gets exactly what he deserves. But seriously, don't listen to headphones at the base of a cliff. So we only have two energy states, the beginning and the end. Now, I like putting I and F here, but I know you don't. So you can use before and after. And I goofed here. That should be I, that should be F. Oh well. There's your starting energy. There's your ending energy. Rearrange these equations, the masses cancel, and you get this lovely simple little formula for the speed of impact. But I know you don't like doing that. A lot of you just really want to plug the numbers in. So if you have to, do that. So let's say I give you these two numbers. And you do MGH, and you get that. Curses. No matter how many times I fix this, it puts the J down here. Drives me mental. Anyway, we're looking here at about 170 kilojoules. That's the total energy budget that's going to show up down here. E and E are the same, beginning to end. So the kinetic energy is this. If I rearrange, bring the 2 over, the M over, I get this. There's my speed squared. Hit the square root, and I get 38 meters per second. Highway speed is 28. This is fast. You're not going to enjoy it. Okay? The other way is just to use this formula like that. It goes a lot quicker with much less error. But if you're determined to do it in 2 steps, be my guest until you're comfy with doing it in 1 pass. Now let's compare the dynamic and the kinematic method of doing this. Dynamics refers to forces, and forces times distance are energy. So I can call these sort of dynamic equations as well. We've got mgh equals a half mv squared. We get this. That's how quickly you can calculate speed of a fall if you know the height and the mass. Well, you actually don't need the mass, do you? On the kinematic side, these are your choices. So I'm going to ask you, which side of this table would you prefer? I think you'll agree the left side is probably simpler. But there's something kinematics can do that the energy equations can't. The kinematics include time. So the energy equation will not tell us the time of the event, but it will tell us the speed at the end. If you want to do the time, you have to go back to these. So on this one, having no time information at all, you would have to use this equation to solve. But this is why having these in your pocket are really handy. The real strength of this equation is that path is independent. So it doesn't matter the path these people took. They started off with a given energy, mg, big H, for the large height at the beginning. They dropped down to the bottom of the hill. Then all their energy is now half mv squared. They go up to the next hill. All their energy is now split 2 ways. Potential energy of the height on the smaller hill, little h, and the kinetic energy. The connecting thing between all 3 cases is the energy. E at position 1, at 2, and at 3 will be the same if we ignore frictional losses. So you can now calculate the speed at any position along this path, anywhere you want. All you need to know is what height you're at. You don't need to know the length of the path. And that's the beauty of the energy equations. And we'll move on from there in just a moment.